Hi everyone, my name is Thomas Chaton. I'm a staff research engineer at Lightning.ai, and some of you might know me as Chaton. I'm one of the co-contributors of PyTorch Lightning. Today I'm going to talk about Lightning and how we can actually use this framework to move from models to production AI applications. Oh, just one sec, I think the slides are not loaded yet. Oh, perfect, great. So today's agenda is first introducing this new framework, Lightning. I will talk about abstracted infra, flexible distributed systems, and how this can be used to accelerate the development speed of AI toward building your own ML systems or your own AI products. Finally, I will actually show Lightning.ai and some production application we have built and some built-in components coming with Lightning. So introducing Lightning. So first of all, why now we can see through recent advances in AI that there is a blessing of scale. And if you throw more compute to models, you get state-of-the-art results. So latest state-of-the-art models are in the 100 billion to 1 trillion parameters and requires even more compute. An example is Stable Diffusion AI uses 4K cluster A100 in the cloud to train the models. Distributed strategies. So new distributed strategies are emerging to accelerate training and always require more flexibility. And lastly, from model to AI products, the evolution of AI is accelerating, and yet moving from model to AI products still require cross-functional knowledge, expertise, knowledge, a lot of time, and money. So here are a couple of challenges we tackled and tried to solve. So the first one is really when more compute is required, it's really about abstracting the infrastructure. So AI systems today are really blurring the boundary between application and the infrastructure. So you need them to work seamlessly together without the boilerhead or the connective overhead. For distributed system, building AI today goes way beyond actually the confines of a trainer. You need to have a reactive distributed system that coordinate both compute and data to work together. And I think the most fundamental is really the development speed of building such things, right? Like most AI research today never really becomes a product. It's on GitHub, some people might find them out, but I think we really need to optimize the time which is spent from going from a simple AI, from a simple idea to actually building something useful and valuable for users. So today we are introducing Lightning, which is this new framework. So Lightning.app is a novel framework to manage compute data and more. It seamlessly integrates with PyTorch, and it really enables to move from model training to building a production AI application. You can get the Lightning by just doing pip install Lightning. So inside of Lightning, there's currently two namespaces, Lightning.PyTorch, which is previously known as PyTorch Lightning, which is a framework providing free abstraction, trainer, Lightning module, Lightning data module, which really enables to organize your PyTorch code and train at scale through the trainer. And we have this Lightning.app, which is all those new abstraction, Lightning.app, flow and work, and compute. So Lightning, really, in the summary, is a rebranding of PyTorch Lightning to Lightning, which contains now Lightning.PyTorch, previously known as PyTorch Lightning, and this new framework on Lightning app. So today I will focus more on Lightning app, and you can learn more about Lightning PyTorch on GitHub. So here's the new abstraction that we are actually introducing. So we have the Lightning work, which is the smallest unit of execution. It kind of behaves as a remote executor. The Lightning flow manages communication and orchestration between Lightning works. It's highly inspired from React. So we kind of bring a lot of concepts from React as a state and this reactivity, and we render to Python to actually solve those primary challenges within AI around building those distributed systems. The last one is Lightning app, which encapsulates the Lightning flow or work to describe the entry point of the systems. So an app is really a tree of components where the leaves of the tree are actually the works. And the flow is really this kind of continuous system which we render continuously based on the state of the works and decide what to do next. So I'm going to actually show a couple of examples of how this new framework can enable abstracting the infrastructure. So let's start with So let's start with simple PyTorch code. So I have a simple NN modules. I have my criterion, I have my optimizer, and I'm just going to do, I don't know why it's, okay. Oh, wait, why is he? Okay, sorry for that, somehow I jumped to the next slide by itself. Yeah, so simple PyTorch code right there just to optimize a simple sequential module on some random data. So the way to actually run that in the cloud very simply with the new framework lightning.app is to, from Lightning, so import Lightning as L, subclass the Lightning work, and inside of the run method, simply copy-paste the code you already had. Okay, so somehow, okay, great. So simply copy-paste the code that we had before directly in the run method. Once that's done, the next step is actually to instantiate a cloud compute. And once it's done, to actually pass it directly to the component. Finally, that component can be passed to the app. I'm going to jump directly to, so here we have the compute. It's going to do that every time. Okay, can I speed this up? Okay, so once we have the cloud compute, we pass it to the component and then to the app. So here we have the component, and finally, that's going to be painful. Sorry for that. Great. Okay, so once we have the app, now we can run the app locally and in the cloud, simply from the terminal. So to run the app, you can simply do lightning run app with a file, and if you want to run it in the cloud, you simply add --cloud. One interesting thing here is apps actually behave exactly the same way locally and in the cloud. So you could actually run the app on your own computer, you could run it on your own cluster, but if you actually require to scale, adding --cloud just takes the same app and run it in the cloud in a fully distributed way. It's actually also possible to use a Lightning PyTorch trainer directly with a framework. So you just subclass the work. In the run method, you just put your PyTorch Lightning code, so the data module, the module. You get the trainer, and you simply fit the model on the trainer. So here again, we have this cloud compute, which is passed to the component. We pass the component to the app, and with the CLI, we can run it in the cloud. But the interesting thing is Lightning App is actually a very flexible and generic framework. So it's very well tailored for training PyTorch and PyTorch Lightning in the cloud, but it also go beyond the confines of training. So lightning.app.components provide already a lot of built-in components. Here I'm actually covering the Python server. So this one has two hooks, for example, setup and predict. You can simply provide your module, load your module in setup and in predict and all the request. Again, you provide a cloud compute and a build config to the component, pass it to an app, and with a CLI, you can run this in the cloud. This component actually comes with a built-in UI, so which actually shares the code you can use to make a query to the component. So at the high level, a Lightning work really organized Python code, so you can easily run it in the cloud or locally. So if you run it on the cloud, it will be on the hardware, which is actually defined by the cloud compute. So a work really works with any frameworks in the confine of Python, and it's actually possible to use other language than Python. It's very easy to use, and it works locally in the cloud in the same way. So any Python code can actually be put there. So now that I've actually covered the smallest unit of compute, which is a work, I'm actually going to show that by using this very reactive mechanism with a distributed state between the component, we can actually write very flexible distributed system. So I think one which has been extremely complex in the past is multi-node training. So PyTorch Lightning, or the Lightning trainer, already handles multi-node training, assuming the infrastructure has been properly set up. But setting up the infrastructure until now has been extremely complex. So here's actually how it works with Lightning App. So we have a multi-node component. What you will need to do is subclass a walk, overrides the one method. So what the multi-node component is going to do is actually spin up all the nodes, do all the wiring, and give you the main address, the main ports, the num nodes, and the node rank, so you can actually decide what you want to do next. So you can run actually any distributed code just right there. If you want to use PyTorch, you will probably like spawn the processes. So here we actually have the multi-node component. You can provide your own custom component, and that will run in the cloud here on 32 GPUs. But I think what's really interesting here is it kind of looks simple on the surface, but I think it's also important to check inside how complex it is or not, right? So let's quickly review the multi-node component code. So here is actually the init method. It takes a walk which was implemented by the users, customized by the users, the number of nodes, and the cloud compute. And its init method is simply going to create a list, an empty list of walks, which will be instantiated later on. So here is actually the interesting part, right? So remember that the run method is being continuously called, like very similar to React. So the first thing we will actually do is create the walks, right? So we are going to iterate through the number of nodes, and for each node, we're actually going to instantiate a walk. When we call walk.start, that's actually going to start the machines in the cloud. So here, if I had like node 8, now we have like 8 machines actually started in the cloud. The state of the walks, even if they're remote, are actually synchronized in the main machine, which is running the flow, which means that I can continuously check the state of the walks and decide what to do next. So here I'm actually saying, until all the machines are not started, just wait there. We need all of them to be there to actually start doing the multi-node training. So when all the machines are actually ready, which means they have properly set up, they have an IP address, they have a URL, and they can communicate with each other, the next step is to actually run the user code, which has been implemented in the run methods. So here we are going to iterate through the nodes and provide the IP address and the port of the first node to all the others, which means that if you had your own PyTorch code, you could actually create your own progress group, set up all the distributed things, and actually do multi-node training in just a couple lines of codes. Finally, when all the works have executed, which means like the run method and the training is terminated, you can simply do .stop, and now all those machines stops, right? So what's really interesting here is as the state of the remote components are synchronized to the flow and really comes as deltas and events to the flow to re-render or to rerun, the flow can really decide what to do next based on state changes. And yeah, that's simple. The entire multi-node component is only like 60 lines of code. And I think what's really important, it's simple on the surface, but also importantly under. So this multi-node component could actually be extended to add further functionalities to minimize costs in the cloud, like elastic training or even fault-tolerant training on preemptive nodes, for example. And those would be just adding a couple of lines of code to check the status of all those different machines and decide what to do next. So here's actually an example with a built-in Lightning trainer multi-node component. So to do multi-node training in the cloud now, you just need those lines of code. So you just override the walk. In the run method, you put your Lightning trainer code. And then you just wrap that component into the Lightning trainer multi-node component, specify the number of nodes, the number of GPUs. And now you're going to spin up 8 nodes with 4 GPUs each, and all the training is properly wired up to actually do this 32 GPU training for you. OK, so let's move to accelerated development speed. So what's really interesting is the walk and the flow are really those fundamental abstraction which enable to create those higher level of abstraction like components. And our target, our goal is to provide a large ecosystem of components which really removes the engineering boilerplate to build ML systems or actually AI products. So one thing which is very important when you have a system is to find an easy way to actually interact with it, which means like you need to have a UI. So the Lightning Flow proposes configure layout that you can simply override. And you can provide a couple of tabs, so a name and a URL. And every component within the framework has actually a URL. So you can embed them as iframe directly within your app. That supports any Python web UI, JavaScript framework, and I will show a couple of examples further down. But what's really interesting is you could prototype something with Gradient or Streamlit, and as soon as everything works as you expect, you could actually move to React or something more mature to get your product to the next stage. So here's actually an example of this code translating into the UI, right? So here I have 3 tabs, a link to OpenAPI. I have an object viewer, which is actually running a notebook server directly within a work, and some training logs on weight and biases. And I will generate this UI here with a couple of tabs. In the first tab, we have the blog post. In the 4th tab, we have the notebooks. And in the 5th one, we have the training log. So you can actually have a couple of services in the same place working with each other. Also, an interesting thing is usually those systems need to be interacted with either for UI or CLI. So the framework also provides a very simple way for an app to define its own CLI. The next thing you could do is actually connect to this app, download the CLI, and remotely execute its own command. So here I have there's a simple loop called configure commands, and you can map a command CLI side to a server-side function execution. So here I have a simple increment-decrement, which modifies the state of the component. What I can do next is connect to this app. So here is my app running locally, but it could be the same when it runs in the cloud. If you were to do lightning.help, you will see the command associated with this app, and now you can actually interact with the app dynamically. So here's a very simple example actually demonstrating this behavior, but the idea here is you can actually create very complex services in a very minimal way. So I'm going to jump to some real-world production application we built and also some built-in components. So for people who have their computers and want to do it as I go, you can simply go to lightning.ai apps, and here are a couple of steps. You create your own account, you will get some free credits. You can go on the app gallery, and if you click on an app, there will be 2 different ways to interact with them. So the first one will be trade for free, the second one will be clone and run. So you can actually see by yourself this thing works. All the examples we have here, the code is open source, so you can actually check by yourself how this thing works under the hood. So the first app I want to show is actually, and I will jump to the app which is actually running live. It's actually an AI product which is called Muse, and it was built in less than 2 weeks by like 3 engineers. It's using Stable Diffusion 2 under the hood to generate images from prompts. And here are a couple interesting properties for this app, right? So first, it has a work which shares Stable Diffusion 2. Which is then being passed to a load balancer, which is completely written in Python. So this app is actually able and optimized for Stable Diffusion, but scaled to 300 users, concurrent users. The UI is actually in React, and it's mobile responsive. It has a persistent storage, so people can actually interact with the app, download the things. So that's one app. The second app is actually called Echo. So this one is actually kind of interesting because it was built by a single engineer, Alec Medler, which used Whisper from OpenAI to actually generate subtitles for YouTube videos or directly from the microphone, right? So one thing interesting to know here is Alec is actually a front-end engineer, so his specialty is React. Before getting there, he didn't really know about Python and really learn it as he went through, right? So the main properties of this app are really that it's using a load balancer in Python, so it can actually scale to 100 concurrent users, all having their own space. He worked primarily on the React UI and mobile responsiveness. So this app is actually able to support multiple users. So we have one component, which is actually a database, which abstracts entirely the concept of a database that he's using inside of his app. So he can actually seamlessly control the AI inference, but also store all this information for the user to consume it. Okay, and the last app I wanted to show, it's more a platform tool than an AI product. And this one was built in around 2 months of work by 3 contributors. It's completely written in Python, and I think it demonstrates the best practice on how to build kind of advanced apps. So these apps enable you to launch your own experiment and sweep directly from files, right? So as the framework is extremely modular, starts by having this tree of components, the idea was we started by a component which can run a script. Then we build a component which can actually run a script in a multi-node way, which I presented a bit earlier. Then we created a component using that component to do like a sweep across as many machines as many experiments the user wants, also like customizing the optimization with up to 9 and so on. And finally, we wrapped all of that into an app with its own CLI so people can launch sweep directly from their own files. So this app provides a CLI for users to connect to, a React UI, multi-node, multi-GPU sweeps, a persistent database. And what's really interesting is this app can be very easily adapted because it's fully written in Python. And then the component gallery, so when you get on the UI, and I will make a jump soon, you will be able to find components to actually jumpstart this development. So a component is really a self-contained functionality made of flow and works, usually open source. And what's really interesting is like any use case can actually be supported, from data labeling with, let's say, like 51 and Label Studio to large-scale serving with Prometheus and Grafana as you might want to use them. So I'm actually going to jump to Lightning.ai. So just one sec. Yeah, all good. Oh, great, everyone can see. Okay, so when you land on Lightning.ai, you get to this website, so building models from AI to products. So here you can actually see the first example I showed, which is by overriding the run method of the work, you can actually run any Python code directly in the cloud. If you click this button after you created your account, so I'm actually going to log in so I can show some of those. Okay, so let's use this account. I think I do have some credits. Let's see. Yeah, okay, cool. Yeah, so all those examples are actually runnable. So when you, great. So when you click here on the code, the app is actually starting. So here we have one work and one flow, so two machines actually being spin up. And we can see live actually the entire system being pulled off. When the app is ready, this open app will be visible. This app doesn't necessarily have a UI, but if it did have, you could actually interact with it directly from that. Soon we will also have this ability to edit directly in the cloud through VS Code, so you could edit your app lives, and also have this ability to do distributed VS Code implementation for people who cares about multi-node training. Cool, so while this one is running, I think soon enough, yeah, so here we see that everything just run actually under like, I think let's see how much time it took. I think maybe 30 seconds or something. Yeah, so now like our work actually run, and the app is kind of waiting for its next instruction. So let's quickly jump to the component, to the app gallery. So when you get to the app gallery, actually look like that. We have a couple of apps actually ranging through like a lot of different domains. So I showed this one during the presentation, which was the research the research poster. So if you quickly, oh, this one is down, great. Okay, let's go for another one. Let's check, for example, Echo. Yeah, so Echo is actually the app I showed a bit earlier, which is using Whisper from OpenAI. So you can actually like take any YouTube video and directly get the transcription. What's kind of interesting here is you can actually take this app, deploy it on your own account, and the price of running this app is close to 10x or 20x lower than any services actually offering the same services. So you can really create something which empowers people to get to the next step with what they need. If you get there, you will also see that the GitHub repo is accessible and open source. So for people who have an interest, you can directly jump to the code and actually see how all those different things come together, and all the components can be completely modularized to build like higher level of abstractions. So here's kind of interesting to see that this database, a file server, a load balancer, a way to download from YouTube, and so on and so on. And finally, showing the gallery. So getting to the gallery, you will see that there is a way to launch notebooks, do serving, deal with diffusion models, and so on. OK, I guess I'm done. I'm going to jump back to the presentation quickly. Yeah, so it's really a very generic framework which can be used for all use cases, and our goal is really to remove all the engineering headache which comes at really moving from a simple idea in AI to actually something which provide meaningful value to users. Here are a couple of resources to learn more. You can go on lightning.ai, try all those example and apps by yourself. And you can also go on lightning.ai Lightning, which is actually the open source repo holding the PyTorch Lightning code and a new Lightning app release framework. Thank you very much.